So welcome and Happy New Year to you. This is the second part of our introduction to artificial neural networks. We've completed the first block of the more classical, foundation of machine learning, and we'll move into, networks, how to train them, and the modern variants throughout this last second block. Let's recap for a couple of minutes what we've discussed last year. So we introduced you to multi-layer perceptrons. A perceptron here is one of those circles. It's basically, so the activation or the output of one of those, let me just switch to my pointer. So the output of one of those units here is just the weighted sum of all the input variables plus a bias term B. And you will usually find this expressed as matrix W bar, which is the matrix of all weights expanded or extended by this one column that contains all the B's to each of these output units, or these hidden units here. Yeah? And so you'll find this, of course, also for the second layer. And now in neural networks, we have no perceptrons anymore, because perceptrons had the step function. Yeah. So if the weighted sum of all the inputs was greater than a certain threshold, then the output would be 1, and otherwise 0. And in ANNs, we typically use activation functions that are smooth, or at least back in the day, we used mostly sigmoid or 10H functions. So the sigmoid will be shown in one of those later slides, but the sigmoid enables us now to train the network in a way that we will discuss today. Now, let's just go back and try to remember what those neurons do and what they kind of represent. So an artificial neuron, as we discussed, collects all the weighted inputs, sums these up, pushes these through a nonlinearity like the sigmoid function. And looking at this, so W transpose X, so the dot product of the weights with the inputs, is something that we should be familiar with. This is something that can be interpreted as a similarity measure, right? Because this number here is large if W and X are pointing into the same direction. Yeah. So the output will be close to 1 if this dot product is 1. Yeah. So this neuron detects certain patterns in the input. And this shouldn't be new to you. We had this in logistic regression. So one of those neurons implements one logistic regression, one linear division of the space. Yeah? Although we do not have any thresholding, so we don't know in the hard way, which part belongs to the positive and to the negative half space. But so all the mechanics before that are logistic regression, and in a neural network we have many of these. So look at this example of how the bias term plays a role in determining the positive and the negative subspace. But this is just a recap from previous lectures. So since each of these units detect certain input features, we can have many of these, right? So one looks for a certain feature 1, and the other one looks in parallel with an own set of weights for other features. And so if we go deeper, those units here can combine the previous layer features into patterns that they detect. So the outputs, yeah, and this, for example, is an image classification network. The outputs then can use those high-level features that consist of low-level patterns, yeah, or that represent low-level patterns. These output neurons can combine these features and reuse those features, and that's basically what's the result of a learning process, right? So those weights here, all those connections, are the result of a training process. And the cool thing is that we just define, this is the input and this is the output for many of these data samples. And through learning, the network finds those patterns each of these neurons represents. Today, so we're going to talk about this learning process. So how do we train networks? We'll learn about a concept that's called loss landscape. We'll look at a method that's called gradient descent. We'll look, and that's, I guess, the most important part today, on an algorithm that's called backpropagation. And we'll conclude with ways how we can use backpropagation to find the optimal configuration of our network weights and biases. So learning is really, for your network to find the optimal set of parameters that I usually try to imagine as many knobs that you can tune, and thereby, altering the result of your network, right? So given an input image and a classification that the network should yield, tuning one of these parameters will have an effect at this output. And now imagine trying to find or tune all those parameters and find an optimal outcome. This, for an audio engineer, often really means manually tuning those knobs, but we'll find today that it's much easier to do this in an automated fashion, given a data set that is full of images or whatever, data points that usually have a very low level of abstraction, right? So in images we have pixels, and each of these input variables has a value that doesn't mean or that do not represent high-level concepts. It's just a pixel. It's a brightness. So we'll typically have high-dimensional inputs, so many of these pixels. So millions of these input variables get in these networks, and then they have to be processed to produce something that has high level of abstraction, but uses only a few numbers, low level or low dimensional outputs. Good. So how do we approach the training? Well, the first step we have to take is find a way to quantify what is a good setting and what is a bad setting. Now we need to quantify how well the network already represents the data set that it was given for training. So we usually have different output categories in a classification task, and samples that we could put in the network, and then the network produces, let's say, this output here, and then we will use the output and the given target. So that's the label that the human provided for this image here in this case, and we'll look at the discrepancy between the output and the given label. And obviously, doing that for only one image isn't enough. We need to do this, well, basically for all images in the training set to have, to be able to quantify the exact error that this network is producing. So we could, for example, use network output minus the target, and then do the absolute value for this, and then sum everything up or average everything, right? So then we have one number that represents how good or how bad the network's classification actually was on the training set. Now, in the following, we'll use something that's called computational graph. So the network itself is already a computational graph, right? So we have numbers flowing from like input units to hidden states, hidden units, using those connections, and they can be weighted. Yeah, and in those nodes we'll find functions, activation functions. It could be anything from, like we saw, the sigmoid, or could be as simple as summation or multiplication or any function actually, right? So that's called computational graph, and the error produced by the network could also be represented in a computational graph. So consider those output neurons here with the sigmoid activation function. They could feed their prediction y into these individual error nodes, and they, like we just saw, compare this output to the target. Yeah? So T would be a vector for each output class, or that contains for each output class the probability. And now for each individual output class, we compare this to the output of the network, square this, and for convenience reasons, we multiply it by 1/2. You'll see very, very soon why that is. And then we would be summing up all these results to obtain. Now, let's first think of what our goal in network training is. We have super high dimensional space. I mean, I've drawn here 2 of the parameters, but basically what modern networks have are sometimes hundreds of millions of parameters, weights, and biases. And for each of these settings, we can compute a network error for all the samples in the training set, and put this in this loss landscape. Yeah. So the loss landscape is the error, or sometimes we call loss, over the space of parameters. And now the goal is to find a combination of parameters, of weights and biases, that minimize the error, right? So whatever architecture we have chosen, whatever training set we are given, if we find this combination of parameters that gives us lowest error, then that's the solution we're fine with, although that doesn't tell us how good and how bad it is. It's just the best solution to the learning problem. So remember, we have easily many, many hundreds of millions of weights, and we can't do this manual tuning, right? So we can test all different combinations. We have to devise an algorithm that tells us, maybe when we start here, where to go to end up in a region that yields minimal error. So, and learning really means walking downhill. So let's start at this point here. What we'll do, and that's why this method is called gradient descent, we use the gradient, which is a vector. Yeah? So the change of the error over a change of the weights is a vector in the space of all the weights. Yeah? That points into the direction of the steepest ascent. So this is where the slope is maximum. Yeah. And obviously we don't want to go upwards. We don't want to climb the hill. We want to descend down to its minimum. Yeah. So what we want to do is we want to compute this gradient for one step, yeah, for an iteration that corresponds to a certain location that we already in, or that we are already in, and then we want to take the step and then compute the gradient again, right? So our weights for the next iteration are the old weights minus some learning rate lambda times the gradient, and the gradient at that step here. Yeah? So what we want to do is we want to slowly but surely walk down and be efficient. So that means we do not walk sideways. We walk in the direction that locally shows us this is the way down, the steepest way down. Now, how do we do this? Well, what we could do is we could look at our network, and let's just consider this very small thing here. Look at every weight and change it by a small amount, 0.01 or something. And then look how much the error has changed. So this is what we call, computing the gradient numerically, because that's exactly what it is, right? So the change of the error over the change of the weight. And then we could do this for all the weights, and then come up with a vector that tells us how to change those given weights. Now the problem here is that this is very, very expensive. So think of big data sets, image data sets, for example, ImageNet. They come with 14 million samples. So we need to do this not just for all the parameters that could be, here in this example, it's a small network in today's standards. But we don't have to do it only for those 23 million parameters. No, we have to do this 14 million times for only one step. And then we have to do many hundreds of thousands steps so we can reach this minimum. So this is just too much. Huh? So problem setting here is, given our network, we can write down the computation, which is the weight matrix times x, and think of these weight matrices as the extended ones with the biases in there as well, and the x's are augmented by an additional 1. So we can write this down, but now how do we determine the gradient, right? So the derivative of E over the changes in W. And simple networks probably would work, you know, or we could do this for simple networks by writing this down and writing this derivative, this partial derivative, you know, using the rules that we know. We could write this down analytically, and then we have an equation that we could use to compute the gradient. And that's not what we do on paper, but in a way we determine this the gradient analytically using this algorithm called backpropagation. And that's a paper that's pretty old, has been cited so many times. Basically, most networks are trained using this algorithm. The idea here had been described earlier, but everybody cites this paper because this was the first paper that used the idea that had been described earlier in the context of network training. But really, backpropagation works for any computational graph. So it doesn't need to have neurons and, you know, sigmoid activations. You know, like I said earlier, this would work in any computational graph without circles, right? So without recurrences. But for this, we'll learn about a trick that we can do, and then can still use backpropagation. Good. So backpropagation relies on the idea that we can divide our complex network into parts, right? And so think of our network as a chain of activations, which basically it is, right? So a sequence of function evaluations. So the output y is function f of the output of g of x. Yeah, f of g of x is y. So now what is the derivative of y with respect to x? Well, we have to apply the chain rule, which states we use we multiply the derivative of the outer function f prime at the input g of x times the derivative of g at the input x. No? So this is simple chain rule. Now the idea in backpropagation is that the complex network can be seen, or can be seen as a sequence of function evaluations of simple activation functions. Like we saw, one of those simple examples would be the sigmoid. And so the application of the chain rule states the gradient with respect to the input is this the derivative of the sigmoid, which I'll show you in a second how this looks exactly. So sigma prime of g of x times g prime of x, and now g is a complex network and could be further dissected into simpler or simple functions that we know the derivative of. So the chain rule can be applied because we know what the local derivative for each of these activation functions is. We don't know what the complex derivative g is, but we can divide this g further and cut away all those simple functions that we know the derivative for. And the cool thing here is that this is possible because we only have to know two things for each of those local activations. We need to know, well, in this case, z prime, the derivative of this specific local activation here, and the input, which was h of g of x. Yeah? And of course, we need to know that for all the different parts, and that's the idea of backpropagation. So we just go, through this chain of activations and multiply the derivative of each of these activations at their input. So whatever entered here, whatever number entered here, will be put into the equation for the derivative, and then we just multiply everything step by step until we reach the output, and then that's our derivative, our gradient. Yeah. So backpropagation works in two steps. One is a feed-forward step, in which we compute all the intermediate activations and also evaluate our derivatives, all local derivatives. And a backpropagation step, in which we collect all those derivatives to compute our gradient. Yeah. So let's assume we have two functions, g and f. So x is being fed into the network. We have to compute g of x because this is what will be fed into the next function, f. And here we compute f of g of x. And then that's the result of the computational graph. But we also use x to compute g prime, the derivative of g, at location x, and use g of x to compute f prime of g of x. And we store these, actually 4 numbers, in these nodes. So in the backpropagation step, we can collect these. Yeah? Or actually just 2 of these 4 numbers, because we will pass through those nodes, multiplying those derivatives, right? And then we get exactly what we were supposed to get, f prime of g of x times g prime of x. We start this backpropagation step, by feeding in a 1, because that's what we do to not lose or alter our values here. And now I'm going to show you different network motifs, architectures that we will find, and then I will show you how this really works in a small example. Now, what about connection weights? Well, in the feed-forward step, a weighted input x results in the output of this rather small computational graph that is wx. The derivative of this output with respect to the input is w. Yeah? And that's exactly what we do. We multiply whatever is backpropagated. So in this simple example, we should start with 1. But it could be something different. If this edge is somewhere deeper into the network, we multiply this times the weight, and come up with the correct solution, w. So what about multidimensional inputs? We often use, this scheme here. So an array of input variables, x1 through x3, for example, and they all get summed up in this summation node, and the result is x1 plus x2 plus x3. Now, what is the gradient, so the partial derivative of this expression with respect to the inputs? Well, it's just 1, right? Because this expression, you should be able to see that, right? Now the rule in backpropagation is that whatever comes from the final or the later layers of the network, whatever gradient is backpropagated through this node will be multiplied by 1, producing the correct output for this small example. And what about multidimensional inputs for any f? So the summation function is really a very, very simple one, but it could be different, right? So let's think of any f that takes three inputs, x1, x2, x3. Now, what we do is we have to store the partial derivative of this function and evaluate these at the input. And then each of these results will be passed downstream, or actually upstream is this, yeah? So what about parallel processing? This is also what we will see. So the output of this motif here, of this pattern, is f1 of x plus f2 of x. We know what to do with the summation node. So the 1 is passed through this, multiplied by this 1, or any gradient that was already calculated before that is propagated through this by multiplying this by 1. And now we collect the derivative of these individual functions at their input, multiply this with whatever has been backpropagated through here and through here, and then they get summed up, right? So each individual contributions will be summed up, and this makes sense, right? So if you think of how x, the input, can affect this output, it's exactly through each of these functions, yeah? So the effect on the overall is the sum of the effects on the individual parts. Now let's revisit the question that you may have asked yourself. So why are we computing the gradient with respect to the input and not with respect to the weight? Well, that's basically the same, right? Because you can think of the network through which we want to backpropagate the gradient as an input x times a weighted edge, and that's the w that we want to compute the gradient for. Yeah? But we can also and by using backpropagation, we come up with the gradient f prime times the weight, right? So that's the derivative, the gradient of the network with respect to x. But we can switch x and y, x and w. So w now is the input, and x is the weight. And that doesn't change the network's output, right? It's irrelevant how you put this. And now the backpropagated gradient will be multiplied by x rather than w to obtain df over dw. Yeah. So let's have a look at a simple example. We have 3 input nodes, 2 hidden nodes, and 1 output node. We have connection weights, W, and they have the superscript that denotes the layer. So this one here in parentheses denotes the first the first weight layer, and the 2 here in the superscript denotes the second weight layer. W11 means the connection between unit 1 and in the input layer and unit 1 in the hidden layer, right? So W12 would be this connection, W21 would be this, W22 this one, and so on. Same notation for the weights of the second layer. Now you can write down the equation of the network's output. So Y would be the function f3 for f1 times its weight plus f2 times its weight. Yeah? And of course we have to evaluate these guys at their weighted inputs of the inputs x1 through x3. Now let's try to come up with, by looking at this equation, let's try to come up with an analytical gradient here. Yeah. So let's try to find this for this weight. So we want the partial derivative of this function f3 with respect to the weight W32 of the first layer, this one here. And so the first thing that you should notice here, that x2 and x1 have nothing to do with this weight. Yeah? So the only thing that should pop up in the solution is x3, because it will determine also how strongly W32 affects the output f3. And f1 has no role. Yeah. So since W32 here does not connect to f1, so the only path, the only way it can affect f3 is through f2. We expect that our gradient looks such that there's no f1. Yeah? So let's have a look at this function, at this description here. If we want to come up with the partial derivative of this thing with respect to W32, we see there's no W32 in this part, so this will vanish. The only thing that will stay here is this one. So we have to apply the chain rule. So first we'll find the derivative of this inner function, which is this x3, right? So the only thing that is not relating to W32 is this last part here. So x3 times the derivative of the outer function, which is f2 prime at this local spot, right, at this local input. So this is exactly what we have written here, right? And then this needs to be multiplied by the weight times the. So we again have this inner function here and the outer function. So the inner function has been we have put the partial derivative of this function here by by W21 and then times f3 prime. Good. So this is what we, knowing the rules of derivatives that we learned in school. But I'll show you now how backpropagation can be used to obtain the exact expression up there. But let us first simplify things, because F1, F2, and F3 usually look the same. So I just kept them so you know where those functions go. But in the end, we'll have sigmoids, sigma here. And we'll simplify the output of this first activation here, of this first unit, and we called it O1 with a superscript of 1 in parentheses. That means the first layer of activations, of outputs. Yeah. So that's for the first unit, for the second unit, and that's just sigma of all the weighted inputs and the other the other inputs for the second unit as well. And the third, so the output unit, is also called O1, so that's the first and only output unit in the second layer, and that's just the weighted sum of those outputs. Yeah, so this is just to simplify those, or it's a notation to simplify those slides here. But since we want to do backpropagation, we need those outputs as well, and we also need, remember what we need? We need to evaluate the sigmoids' derivatives at their inputs. Yeah, and that's what we do as well. Oh, I forgot something. We need to also add this error node here, right? So assume we have just a one-dimensional output here, and we compare this output O1 to this given target T, square it and half it. And now what we need to do is we need to store in each of these nodes, in each of these 4 nodes, the derivative of this function at their inputs. Let's do it. So I call this D, like derivative, and use the same indexing notation. So subscript 1 means the first unit, superscript 1 means first layer. Yeah. So, and then the derivative of the sigmoid function is pretty cool, because it's just the sigmoid function times 1 minus the sigmoid function. And since we have already evaluated the sigmoid function and have stored it in O1 superscript 1, we just use this number that we've stored and compute the derivative by, like it says there. We do this for this node and for that node and for that as well, because they are all sigmoid nodes. And this one here is no sigmoid node. It's just a squared error. And and now you see why we used 1/2 times the output minus T squared, because now moving the square to the front cancels this 1/2 out. Yeah, and this is the derivative that we store in the error node. Now, let's do backpropagation again for this weight here. And so we start with a 1. We put this in, collect this number, DE, then pass this through this connection here. It has no weight, so we implicitly use 1 here. Multiply it by D1 superscript 2, and then multiply it by this weight, multiply it by this derivative, and remember, to obtain the derivative with respect to this weight, we need to then ultimately multiply it by its input. Yeah, and that's exactly what this sequence of multiplications represents. Good. So that small example, I think, is something that you could do on paper at home, or pause the video to see if that really makes sense to you. You can also read this book. I think it's one of those early and very famous books about the classical networks. The notation that we have used and the notation that we will see now is taken from this book. And to wrap up everything, summarizing and condensing everything into a compact matrix vector notation, let's review this again. So the feed-forward step consists of using our input variables x, or let's call them O here for output, and don't forget the ones, and we'll use this hat notation again. So this vector is multiplied with the weight matrix, with the augmented weight matrix, pushed through a sigmoid to obtain the output vector O superscript 1, and then the same is then done with the hidden layer activations. They are multiplied with this weight matrix W superscript 2, W hat, yeah. And after applying the sigmoid function, we obtain O superscript 2. So those are the outputs. And they then, like we saw before, are compared to the target in these error nodes. And again, this weight matrix W bar for the first and for the second layer, although they may have different sizes, this is an augmented weight matrix W with an additional column vector corresponding to the biases. We will be using W without the bar in the next step, in the backpropagation step. But in the forward pass, we also store the derivatives. So in matrix notation, we build up matrices D superscript 2 and D superscript 1, and they are only diagonal matrices with these sigmoid derivatives for each individual output. So for example, for the first output neuron, we store O1 superscript 2 times 1 minus that value. Yeah, and for the hidden layer as well, and we have M2 many in the output layer and M1 many in the hidden layer. The errors or the derivatives of the quadratic errors are also stored in a vector called E. In the backpropagation step, we collect in a vector all the backpropagated errors. So the errors all the errors from those error units times this diagonal matrix, which just multiplies these values with their corresponding output unit derivatives, yeah, because there is no crosstalk. It's just the jth output unit connects to the jth error unit, so that's a one-to-one connection. Now from here, so in delta superscript 2, we have the gradient in a vector that corresponds to this output layer. Now to compute the change for a parameter wij in the second layer, we need to multiply this with the output of the hidden layer. Yeah, and so to obtain a matrix, we use this outer product, delta 2, which is a vector, times O hat superscript 1 transpose, which is the structure here. So this is the delta vector, this is the transposed O hat vector. And so the ith value of the hidden units, so that is the output of the ith unit, is multiplied with a jth backpropagated error, which is exactly what gives us the gradient of the error with respect to this connecting weight here. Yeah? Since we have a matrix of weights between those two layers, this product is a matrix, and as discussed before, we need to negate this. So take the negative of this gradient and scale it by something that's notated as gamma here. That's the learning rate. Now, we have to backpropagate this further. So from the delta 2s that are the backpropagated errors until the output layer, we then compute the backpropagated error up to the hidden layer. And now we see that this error is influenced by many output paths. Yeah, so we need to collect all these backpropagated errors in delta superscript 2 through their connecting weight matrices. And I highlighted just one path because we want to see what is the exact change for this one Wij. But what we do is we multiply delta 2 with the weight matrix of the second layer. And we need to transpose this because we are now going back, right? So imagine you had W2 not in a transposed variant, so this would be a tall matrix, yeah. So, and it needs to be like that because you want to multiply the output of the hidden layer to this, and now so each row in W would correspond to the respective row of the outputs, yeah. So but now transposing W, this row would correspond to the jth, so the jth row would correspond to the jth hidden unit. So in this row vector, they are all the weights flowing into the jth hidden unit, back into this hidden unit. Yeah. So multiplying this matrix with delta superscript 2 gives us, for example, this backpropagated error to this unit times this weight plus the backpropagated error until this unit times this weight plus and so on. Yeah. So we collect a weighted sum of all the backpropagated errors into this unit. Yeah, and of course this matrix vector product will result in a vector that we have to multiply with the stored derivatives that we have already organized in this diagonal matrix D1. Yeah? And so this product here will give us the backpropagated error until the layer of hidden units. And now if we look at one specific weight, Wij, in the first layer, we need to take this backpropagated error and multiply it by the input into this connection. Yeah? And that's exactly what we do, like we saw before. So we take O hat, which is the augmented vector of inputs, transpose times this delta 1. So we get a matrix, like we saw on the previous slide, of gradients for each of these weights, and we take the negative gradient scaled with the learning rate, and that's our change for all these parameters. Now we do that for every single sample in our database, in our training set. And doing this just for one sample would probably not give us the correct vector, would probably not point into the correct direction in which we should go. For example, in this direction, which isn't the steepest descent. So we need to integrate. Actually, we should do this over all samples in the training set. And so I tried to visualize this here. Each of these arrows points into a direction. So that's the delta W, right? So that's the vector in which we change our parameters. And averaging this gives us a better estimate of the correct direction. Yeah? But doing this for the entire data set, for each step that we want to do, is really expensive. And that's one of the problems that you will notice. It makes things slow. And also, memory consumption is high because you need to have all your data in memory, right? So you don't want to load all those, I don't know, images or CSV files from disk. You usually have this in memory, and having 14 million images in your RAM isn't feasible, isn't practical. Yeah, so, but there are more problems. One is, for example, that gradient descent will get stuck in local minima. Yeah, so if you have a loss landscape that looks like this, and you start close to or in the attractor basin of a local minimum, you will walk into this. And although in practice this isn't really a big problem, that's still something you need to be aware of. Yeah? And why isn't that in practice a problem? Well, we'll see some solutions of what to do with the gradient to not get stuck, but also think of your loss landscape is living in a huge space, yeah, and having a local minimum that in every direction is really a minimum, that's highly unlikely. So there will always be dimensions in which you can like get away, yeah, get out of this region, and but yeah, so what actually is a bit of a problem is plateaus. So think of your sigmoid activation function. At some point, those get saturated, right? So if they have a lot of activity collected through their incoming connections, the output will be close to 1, or if it's really very, very small, right? So large negative values, you will have values close to 0. And even changing a lot in input doesn't really change the output. So this is true for the local activation function, but this is also true for the error at the end of this network. And it's really hard to get off because your gradient will be small, right? So the value that you come up with, the change that you add on to your weight, will be very, very small. Yeah. So you can even run into numerical into your numerical precision, and then there will be no change. So you will get stuck on a plateau, even if it's not perfectly flat. This could happen too, well, but then there's no gradient information at all, and you won't be able to even theoretically go from there into the right direction, because you don't know what is the right direction. So one of the very simple solutions here is we use randomness and a little noise, and reduce the number of training samples to approximate the gradient. So we pick a number for the size of our so-called batch. So we'll probably, you've heard of this mini batch or so. We decide to collect 32 or 64 or whatever samples into one of those mini batches, and do the feed forward and the back propagation step for each of these samples, and then we integrate. So that means either summing or averaging all those 32 or 64 gradient updates, and so that's resulting in good enough estimates of what the real gradient direction is, and the path that we walk looks a little wiggly, but in the end it's faster, and this wiggling may even help freeing the optimization out of local minima. So I'll leave you with the formalism here. You can read this. Just pause the video for those who care about the exact details of this. So to summarize here, stochastic gradient descent speeds up training times by introducing randomness. We are less likely to get stuck in minima, in local minima, and we can reduce memory cost, so that training with huge data sets is made possible. Okay, let's have a look at a couple of variants of the original vanilla stochastic gradient descent. The first customization, let's say, of the update rule is called momentum. So the idea here is that the path that the optimizer is doing is not just a function of the current gradient at the position in weight space or in parameter space we have at our current step. It's informed by the history. So, the way we have moved. And we do this by integrating past gradient steps or gradient vectors into a variable that's called v, so like velocity. So new here is some hyperparameter, s is this gamma here. So they define the let's say a relative proportion of the gradient information at time t and all previous gradient informations. So the velocity here kind of gives the next step a bias towards the directions that have that we have already taken, right? So for example here in the right there's no momentum. SGD in the vanilla formulation would get stuck in this because the step at a certain point is only a function of the gradient here, and even if there was if we weren't stuck in the perfect minimum, we won't be able to escape this. But with momentum, the optimizer will have a memory of past optimization steps into this direction, and running up the hill would diminish our variable v at some point. But if we had enough velocity going into this minimum, we will get out. Yeah? And then hopefully fall into the correct global minimum behind this one here. So in RMS-prop, we have a similar idea. We have a variable called S, and this is basically an exponential average of old gradient information and current gradient information, but we use the square, so element-wise, for all those gradient values for each of for each individual parameter, so beta, for example, could be 0.9, so 90% history plus 10% current gradient magnitudes, let's say. Yeah. So here, really, we do not care about the sign in which direction a parameter or the gradient points. We just care about the magnitude. Yeah, using the square here. And the weight update for our parameters are now using the original gradient, but we normalize by the square root of our smoothed gradient squares, yeah? Gradient magnitudes. So what does this mean? Well, first of all, it may help understanding where this comes from historically. So there was an algorithm called rprop, and this took only the sign of the gradient. Yeah. So we didn't really care whether this dimension needed a huge step and this dimension a small step. We only did one like unit step. But for reasons I don't want to go into detail here, this didn't work for mini batches. And so RMS-prop, uses like this history of mini batch updates in S, and comes up with, through this normalization, with basically a very similar customization step, right? Because dividing the square root of the smooth version of the square is basically giving us the sign, approximately of the gradient. Yeah. Okay. So in effect, also highly fluctuating dimensions are reduced, right? Because we only care for the sign. And lost landscapes like we see here, where the gradient does not point to the correct minimum, but somehow perpendicular. Yeah, RMS-prop has been shown to work really, really well, quickly converging to the correct locations. Another popular variant is Adam. So this has been published by Dietrich Kingma, one of my favorite researchers. It's basically a mixture of RMS-prop and momentum, and Max will show you how it works. I think we've seen some of the most important optimizers, and you will be implementing those three, plus vanilla SGD, obviously, in your exercise. So let's summarize. Today you've learned about how to optimize, how to train your neural network. We have not yet introduced you to the modern architectures, and but still under the hood, you know, backpropagation is the method people use to train even you know, very fancy new modern architectures. You know, basically what you will do in the assignments is to implement this all yourself, but in practice obviously people you know, go to different implementations, TensorFlow, Keras, PyTorch, and so on. There's a whole universe of libraries for you to learn or to get to know, and they implement backprop for you. But I think it's very important for you to implement backprop yourself, so you know what those libraries are doing internally. So that was it. Thanks for watching. I hope you enjoyed backpropagation. Please collect your questions, ask them on Monday. Have a great weekend. Stay safe, stay healthy. See you next time.